You go 4, you don't go at all. So, yeah. But the other guy's thinking exactly the same thing. So he would betray you. So you'd go for 2, so you'd each go for 2 years instead of, if you both remain silent, you'd each go for 1 year. So surely it's better to remain silent. Because if you're going to betray him and he's going to betray you, you both go for 2 years. If you both remain silent, you both go for 1 year.
Is this about like the most economical thing, or is this what I want?
It's what you want.
Oh, well, I was thinking that I would betray him because then I would get 3 years or no years if you remain silent. But if I was silent,
Yeah.
I would definitely go to prison, no matter what.
Yeah, okay. So now you're faced with a situation where, say, for example, you do this, and something happens, and then 3 years later, you come back to prison. And you're in the same situation, but this time, the other guy knows what you did last time. And so you do something, and then let's say something happens, everybody goes to prison for a certain amount of time. 3 years later, the same situation arises, and the other person knows what you did both times. So if you've got a reputation for not betraying, then the other individual will say, hey, I don't believe this guy's going to betray me because twice before he didn't do it, so I'm not going to betray him, and then we'll both be better off, and we'll each go for 1 year instead of one of us going for 3 years. Yeah?
But it says that it will not affect the future.
Right. Yeah, so it doesn't. But then if you go to the tit-for-tat game, so, what do you do for a one-time? And there's a whole theory on this, and we're going to not do these. We're not going to go into this theory because we're interested in an extension of the tit-for-tat. The tit-for-tat is the situation where, so the tit-for-tat is the iterated prisoner's dilemma. So now we have an iterated prisoner's dilemma, and people know how you behaved in the past. And so there's this idea in evolutionary theory about the evolution of reciprocal altruism. There's also the idea of paying forward. You do something now in the hopes that in the future somebody will say, gee, you're a good guy, therefore I'm going to be good to you. Why are we altruistic? Why do we put ourselves on the line? Why do we risk our lives to help somebody else? Or why do we give up something to help somebody else? How does this work? So evolutionary biologists are interested in understanding this. In the same way that the iterated prisoner's dilemma is a dynamic equation or dynamic system that's got discrete points in time. You play it once, you play it twice, you play it 3 times, you play it 4 times. So evolutionary game theory using differential equation models makes this problem continuous and provides a framework for understanding the hawk versus dove game. So let's return to that. Are there any questions so far about this? So I don't want you to know the hawk, I don't want you to know tit-for-tat and the prisoner's dilemma as part of this class for examination purposes. I think it's nice and interesting for you to go and read the wiki stuff, and to the extent that you're interested, you might get into this. And there's a lot of interesting stuff on the tit-for-tat problem and its use in the social sciences and economics and social sciences, but also in evolutionary theory for understanding things about altruistic behavior. We may seem that we behave altruistically now, but in the future, it's kind of the altruism like a pay-forward where everybody knows you're a good person and they can trust you on something, and that pays off later. So let's go to the hawk and dove and the replicator equation. So we come to this payoff matrix. And this payoff matrix says that if little a are doves and big A are hawks, and there's a payoff V. So when we come together, like there's a resource and we come together, and there's a payoff V for taking this resource, then if we're 2 doves sharing it, we obviously each get half. That's the deal. And there's no cost to fighting. Now if a hawk meets a dove, the hawk indicates to the dove, if you try to take anything of this, I'm going to trash you. So, and the dove, looking at the situation, says, well, I am smaller, and I will get trashed, so this doesn't help me. So what I'm going to do is I'm going to back off, and then the hawk gets V. Now, that's when a hawk meets a dove, or a dove meets a hawk. But what happens when a hawk meets a hawk? When a hawk meets a hawk, then they get engaged in a battle. And eventually one of them wins. Or they both may be able to get some of the resource. If they fight first, and they sort of grab bits of resource, and they're kind of equally matched, then by the time they've each got half the resource, they've also got to pay some cost for having been involved in a battle. If you measure everything in terms of energy, you can say if there's a resource there, I go get it, I can get all the energy out of it. But if I have to expend energy fighting to get half of it, then I get the energy out of it minus the energy lost in fighting. So you can bring this down to energy terms. You can bring it down to economic terms where, these are 2 people who agree to share something. These guys, the hawks threaten to get lawyers and the doves don't. The doves agree, we can share this. The hawk says, if you don't back off, I'm bringing in my lawyer. So you back off. But when the hawk meets another hawk and they say, if you don't back off, I'm bringing in my lawyer, they both bring in their lawyers. And in the end, the judge says, I'm awarding you each half. And so this is like a divorce. If you're going to get divorced, should you be a dove or should you be a hawk? Obviously, you're going to do better if you're both doves, yeah? Okay, so there's different ways of interpreting it. This is kind of a general theory, and it says on average, each will get a half. But it may be that so you're averaging over a population. So on average, each gets a half. So that's a good question. But you're averaging over all hawks on average. And so if you put these into the replicator equation, and remember the replicator equation had a general expression like this with the different p's, then you get an equation that looks like this. So what we want to understand is what happens for different values of C and V, for different costs and different rewards. And so you can analyze the relationship of the reward to the cost. So the question is, if I have a system like this, will the hawks exclude the doves? Will the doves exclude the hawks? Or will hawks and doves be able to coexist in some way? So who thinks the hawks will always exclude the doves? Who thinks the doves will always exclude the hawks? Okay? Who thinks they'll be able to coexist in some way? So all 3 answers are correct. The real answer is it depends on the relative values of V and C. And so we'll go to, let's just quickly go to the example. If V is 2 and C is 3, so in other words, it's really expensive to end up fighting. So that if you're going to fight, in the end, you're going to come out with a negative amount. However, it's still good to be a hawk if there are a few doves around, because whenever you meet a dove, you win all of it. The real problem is when you meet another hawk, you lose more than you get. So when two doves meet, they each get something. When a hawk meets a dove, the hawk always gets everything. But when a hawk meets a hawk, they both get something, but it turns out to be negative, because they'll get V upon 2, which is 1, but they'll pay something for having been involved in the fight. And what they're paying for in being in the fight is going to be more expensive than what they can ultimately get. So it's like if you're going to get divorced and you're fighting over $100,000, and the lawyers between the two of you cost you $200,000 in the end, then you know who won. It was the lawyers. So, again, like if you're going to get married, be a dove. Or don't get divorced. Okay, so in order to analyze this equation, we'll come back to analyzing it. We'll talk a little bit about stability theory. So classification of equilibria. So as we said, when you get an equation, dy dt is some function of y, you solve for the equilibria. Yeah, we solved and we said one equilibrium at k, one equilibrium at y. In the replicator equation, there's one equilibrium at 0 and one equilibrium at 1. And the equilibrium solution is stable if f of y is positive for all y near this equilibrium. And it's unstable, so you can read that in detail, but essentially it's stable if you map the points. If you're above the equilibrium, then you move down. If you're below the equilibrium, you move up towards it, then it's stable. On the other hand, if you move away from it in both directions, it's unstable. But if you move towards it in one direction and away from it in another, in that case, the phase line will look something like this. So you can imagine if you've got three equilibria, one over here, and one over here, you might get a situation where this equilibrium, you're moving in this direction towards it. So that equilibrium would be stable. However, if from here to here, we're in a situation like this. This one's stable. This one's unstable. This one is called semi-stable because you approach it from one direction, but not from the other. Did we see an example so far of a semi-stable system in our analysis of any system that we talked about? What was it? What was an example of a semi-stable situation? So think about harvesting, logistic harvesting and constant. So remember we talked about harvesting the logistic equation. dy dt equals ry 1 minus y upon k minus h. Now we used x then. We said dx dt. But I could use y if I wanted to. And remember, we drew the equilibrium and we drew h. So this is f of y, which is this. And here's h. And we said that this equation over here, if this is f of y, including h, so we'll make this whole thing f of y. No, sorry, I've called this, we'll make this f of y, but we'll make this whole thing g of y. So we're talking about the stability of g of y, the right-hand side. And the stability of g of y is going to depend on having two equilibria there. And remember, we said that in this case, it's actually a third equilibrium. And we can move in this direction, or we can move in this direction, and over here we move in this direction, or we move in this direction. So look, if we look at this line over here, that's like our phase line. It's lying on its side. And we plotted out the directions that you move. But we said, what happens when h increases so that it's the maximum sustainable harvest? Maximum sustainable harvest. Then, when you're over here, you move down, but when you hit this, you stop. But if you just the other side, you move down again. So that's a semi-stable situation. So remember that? Okay. So you can read the classification of equilibria. Now, how do we analyze these equilibria formally? Remember we said, what did we say? And I'm going to show you now a formal definition of what we said informally at the time. What did we say? How do I decide if this equilibrium is stable or unstable? How do I decide? Remember, I look at the derivative of the function and see whether the derivative is positive or negative. Yeah? Yeah, so that's for the discrete model. For the continuous model, it's when the derivative of the right-hand side at the equilibrium is less than 0. So absolute value less than 1 for the discrete model, less than 0 or negative for the continuous model. So you must get this clear in your minds for the midterm. It will definitely be asked. Okay. Okay, you tell me what it said. The derivative of the right-hand side of the model. So, okay, so I'll write down the model. I'm going to write it down with x now. The x dt is f of x. X star is an equilibrium, implies f of x star is equal to 0. I look at the derivative df dx at x equals x star and say, is this positive or is this negative? If it's positive, it's unstable. If it's negative, it's stable. And if it's equal to 0, then what? Possibly. It's actually a little more complicated. It means that I can't determine. It could be semi-stable, yeah. But in some cases, it's semi. Sometimes you get highly nonlinear equations where you have to look at the second derivative and the third derivative to really see what's going on. But yeah, that's a sensible thing to guess. But it might be that it's actually not semi-stable, but that it's just like if the right-hand side involves polynomials that are quartic and higher, to the power 4, 5, 6, then crazy things happen. Okay, so you got this? Okay. So now we're going to talk about something that's very important. That's called linearization. And I'm going to take a function f of x. And I'm going to look at it at an equilibrium, x star. So that implies f of x star is equal to 0. Now the thing about we use something called a linear approximation to expand the function f of x around the point x star. Have you heard that language? We linearize, so you should have done this in your calculus course. Who remembers this from your calculus course? Expanding a function f of x around a point x star to get a first order linear approximation. Rolle's theorem, stuff like that. Remember that? It's all in the calculus textbook, but we'll go to this picture. Let's make it nice and big. Oh, that's a bit too big. Let's go to, okay. So a function f of y is the blue function. We evaluate this function at a point. Now we can evaluate this function at points that are distant from here, in this direction and in that direction. So let's go out to some arbitrary point y, and let's evaluate this function at that point, f of y. So if we know what this function is, we can evaluate it f of y. If we don't know what this function is, but we know what its tangent is, then we can say its tangent provides an approximation to f of y at this point. And as you go further and further from the point, the approximation gets worse and worse. If you're going to use the tangent as a way to approximate f of y, by knowing f at y star, you say f of y, in red there, is approximately equal to f of y evaluated at y star, plus this extra bit, which I can get by going a distance y minus y star and multiplying by the slope. That'll give me the height. So from your geometry, you know that the height of this is equal to the slope of this times the distance of that. So that is the graphical picture, but you make an error. And you make an error because the linear approximation overestimates what's happening because this is curving down. If it was curving up, then the linear approximation would underestimate. So the error can be an error of overestimation or underestimation, depending whether your function f has positive or negative curvature. Does everybody understand that? So if we go back to, we can say here that f of y is approximately f of y star plus the increase in height, or the change in height, that goes from going a distance on the horizontal, y minus y star, multiplied by the slope of the function at the point where I'm estimating. And this is a first order approximation. How many of you remember Taylor's expansion? So this is like Taylor's expansion. This is a first order of Taylor's expansion. Then you get second order, third order. So now, this differential equation is complicated, but we can make it linear by replacing its right-hand side. By instead of the function, we replace the right-hand side by the linear approximation of the function. If we do that, we've taken our nonlinear equation and said we replace it by this linear equation, which we assume to be valid for y close to y star. So we say the right-hand side, I can replace f of y by its linear approximation, provided I don't go too far in this direction. Because as you see, as you go further and further, so the error will grow. And the error goes to 0. This difference in the estimate, the difference between this line and this line, goes to 0 as I approach y star. So the error gets smaller and smaller as I approach y star. So what this does is says, if I take this equation, I can integrate it. This is just a linear equation. If I start out at some value, y0, that is different from y star, then I can integrate this equation. And so instead of solving the equation y equals f of y, I can solve the equation, dy dt equals f of y, I can solve this linear approximation, and I can get this solution. And this solution depends on the slope. And if a, which is the slope, is negative, then this bit goes to 0. E to the at, if a is negative, goes to 0, and y approaches y star. If this bit is positive, if a is positive, then this will grow, and y won't approach y star. So this allows you to deduce the following theorem, and that is, suppose f of y is differentiable at y equal to y star, and y equal to y star is an equilibrium of the equation, then y star is stable if the derivative of f at y star is negative, and unstable if it's positive, with no conclusion if it's 0. So that's basically what we've been saying to now. This is how you prove it through a linear approximation. It's not really complete in that you have to, in mathematics, you have to be a lot more careful in this, and you have to make sure that the approximation works what is called asymptotically. We're not going to go into this. You just have to know this result. You don't have to know how to get it. You need to know linearization, because linearization is important. So you need to know that a function f at a point y can be approximated by knowing it at some point y star, and knowing its derivative there, and how far you are from that point. And this is very important in mathematical theory to know this approximation. Okay, so if we do this, here we've got the hawk and the dove game. And we're going to use linearization to classify each of the equilibria. So if we look at the right-hand side of this equation,